Polymers are amazing material. They are in the clothes I'm wearing, the cup of my coffee, my glasses, and they are even inside my body. In this video we will learn how the change of these wonder materials move and talk about some theories that describe polymer dynamics, with a special emphasis on reptation theory. Since polymers are viscoelastic materials, and this important property was one of the earliest motivations for theories of polymer dynamics, we will start our journey on this topic. Let's get started. Polymers are unique materials with unique properties. One of these properties, which is exhibited by all polymers, is called viscoelasticity. Viscoelastic materials exhibit both viscous and elastic behavior when submitted to deformations, and hence its strain response is time dependent. This is a direct result of the long chains that polymers have, and the fact that their chains can also form physical entanglements, much like spaghettis in a bowl. There are many examples in daily life of materials that exemplify this behavior. The dual behavior of polymers when submitted to an external force, known as viscoelasticity, has sparked the interest of the scientific community on answering challenging questions on the dynamics of polymer. If the external force is fast, polymers tend to show an elastic response, while if the external force is slow, they tend to show a viscous response. The close relation between viscoelastic properties and polymer dynamics and change movement has long been recognized. Attempting to answer questions about why highly viscous polymer melts behave the way they do led to the development of milestone scientific models such as the Rao's model and the reptation theory.
Before proceeding to reptation theory, now I will talk about Rao's model, and I have a practical example to let you know how the model works. To represent the mechanical behavior of the material, the subchain clusters are considered to be spring. So the spring subsection has two elements, a spring of no volume connected in series and a rigid bead of infinite modulus.
The reptation model describes the thermal motion of long and linear molecules in solutions or in a melt. The main feature of the theory is that polymeric chains are entangled. Entanglements represent temporary or non-chemical crosslinks that restrict the change movement. If we take a polymeric chain out of a polymer melt, which is often referred as a test chain, we can imagine that the mobility of this chain is constrained by its neighbor chains, and that in order for this chain to move, it will have to crawl along, moving in a snail-like motion as shown in this cartoon. This simple idea is key to the theory of reptation and gave rise to its name. Reptation is not applicable for very dilute polymer solutions where there is not a big number of physical crosslinks per chain. The central idea in the reptation model is the tube concept. The tube is created by neighborhood change as they act as obstacles for the mobility of the test change. This figure shows a representation of how the neighbor change in a polymer melt or solution is replaced by a tube that represents all the steric constraints experienced by the test change. So far in our discussion of reptation theory, we have assumed that the only change that can move in a snake-like motion is the test change, and that the other chains are frozen without the possibility of moving. In a dynamic picture, however, the neighbor change can also sneak out and move away, effectively reducing the constraints imposed to the tube concept and making the tube concept essentially no longer valid. So, how is it that the tube concept remains central to the reptation model? In his seminal paper in 1971, Pierre Dugens showed that the mobility of the chain to sneak out of the envisioned tube is faster than the mobility of the neighbor chain moving away from the test chain, and hence the steric constraints will remain. The tube length and diameter vary with its contour and time and makes the following assumptions. First, the chain test wiggles within the tube over a short period of time. Second, the test tube can only move along the tube and not beyond it. Third, the head portion of the tube can explore any direction randomly. When the head of the chain moves out of the tube, a new portion is added to the tube, while the tail leaves a vacancy behind. This means that there is usually not much change in the length of the tube with time. So, if you want to know more about reptation theory, let's go to the lab. Okay, so to better understand reptation theory, let's first take a look at this simple model made with rubber bands. The rubber bands represent polymer chains. The points where polymeric chains interconnect represent entanglements. This is how polymer melts or concentrated polymer solutions look in a molecular level. Let's take one of the chains as our test change of interest. If we try to move it sideways, its movement will be restricted by the neighbor change. So the only way you can move this particular test chain is to do it in a snake-like motion, like this. This rather simple idea explains why polymeric melts move so slow and can make some good predictions that matches well experimental observations. Making predictions about experimental observations is key in any successful theory. Using reptation theory, we can predict three main parameters that are important for polymers: the longest relaxation time, the viscosity of polymer melts, and the translational diffusion of the chains. To understand the longest relaxation time, let's take a look at a plot of creep compliance versus time. The plateau region at J0 represents the elastic region, or the region where the polymers behave like elastic material, and it is often represented by Hooke's law. The region where the creep compliance increases as a function of time represents the viscous region, where the polymer behave like ordinary liquids, and it is often represented by Newton's law of viscosity. The longest relaxation time represents the time when the polymer's response to the stress changes from elastic to viscous or vice versa. It can also be interpreted as the time it takes for a reptating chain to leave its original tube. High values of the longest relaxation time are the reason polymers are viscoelastic. Using reptation theory, it can be shown that the longest relaxation time is described by this equation, where it can be seen that the longest relaxation time dramatically increases with the molecular weight. That is, it is proportional to the molecular weight to the third power. This result explains why the relaxation time is so slow in polymery liquids when compared with ordinary low molecular weight liquids. Most experiments indicate that the dependence with the molecular weight is to the 3.4 power. For most practical cases, this discrepancy is acceptable. Viscosity is the resistance of a fluid to flow. Fluids with high viscosity take longer to flow than fluids with low viscosity. Viscosity is important for any process involving fluid flow. It can help answer simple questions as how long will a tank take to fill up, how much energy is required to pump up certain fluid, and even to determine the structure of molecules in a solution. As in the case of the longest relaxation time, reptation theory predicts that the viscosity is also proportional to the molecular weight to the third power. Also, in this case, most experiments also show that the dependence with the molecular weight is to the 3.4 power. The coefficient of translational diffusion represents a polymeric chain moving as a whole in the merge. In this case, the reptation theory predicts that the coefficient of translational diffusion is proportional to 1 over n to the power of 2. In other words, the higher the molecular weight, the slower the change movement is. This means that even if thermodynamics says that two polymers are miscible, they will still completely miss very slowly. Experimentally, the coefficient of translational diffusion presents the proportionally predicted by the reptation model.
Polymer chain dynamics have very long history. Today I'll be talking about the development of polymer chain dynamics. Thus, in 1932 and later in 1940, Taylor proposed that elastic properties of polymer melts were attributed to temporary entanglements between chains. In the right hand side picture, you can see the temporary entanglement of two polymer chains. Models developed by Green and Tobolsky in 1946 and Lodge and Yamamoto in 1956 separately considered entanglements in melts as a temporary crosslink, as shown in the right hand side picture. In 1952, Buenge introduced entanglement friction due to snaking circularly motion of chain sliding around entanglements. He showed how an average polymer molecule in a viscous medium gives rise to viscoelastic behavior that is observed in experiments. Prince-Rouse in 1953 proposed a model for linear polymer known as Rouse model. The basis of the theory is that a velocity gradient in a solution of a linear polymer continuously alters the distribution of configurations of the polymer molecules. The Rouse model divides polymer chain into subsections that are sufficiently large to display rubber-like elasticity. The two elements of a single subsection, as can be seen from the right hand side picture, can be represented in series as a spring of no volume and a rigid bead of infinite modulus. The coordinated thermal motions of the segments of the polymer molecules cause the configurations to drift continuously toward their most probable distribution. Edwards' tube model was the major breakthrough in the theory of entanglement polymers. The theory says surrounding chains restrict transverse motion of a polymer. Each polymer is effectively confined to a tube-like region as shown in the right-hand side top picture. Confining tube potential was defined for polymers with permanent topological interactions for networks. Pierre de Guignes developed the concept of polymer reptation. This theory is the most acceptable theory in polymer chain dynamics. In 1991, he was awarded Nobel Prize for Physics. These models suggest that entangled chains move along the confined tubes. Beginners suggested this work may be used in the problem of entanglement effects in unlinked polymer bands. In the right hand side picture you can see the reptation, which is motion of linear entangled macromolecules in amorphous polymer. He assumed the chain is free to move among the fixed obstacles but cannot cross any fixed obstacles. Constraint released take into consideration the modifications of the confining tube caused by the movement of the surrounding chains which form this tube. In 1978, Marshall Dwyer and some F. Edwards applied reptation model to the rheology of entangled polymer liquids. Dwyer-Edwards theories predictions agree well with the measurement of dynamic mechanical in entangled polymer bands. The theory also takes tube reorganization into account.
Focus on individual papers in the literature can lead to the conclusion that entangled polymer dynamics is a subfield of rheology or polymer processing. Yet, it has relied for its current level of achievement on a very wide range of techniques of materials preparation and analysis. Most of the experiment data on polymer dynamics is measured by the rheological measurement of linear response of stress to an applied strain, or equivalents. And the nonlinear response rheology can be a promising tool to investigate the entanglement structure under high strains. But rheology measurement is unable to characterize the contribution of distinct subsets in the chain segments. The relation between tensor index of refraction and stress tensor is testified by the experiment, which the form birefringence is small, and the relation between bond orientation and segment is linear. Although this relation breaks down when the stress causes a significant perturbation of chain structure at the level of cone segment, optical determination of local stress tensor is widely used now. Neutron scattering is a powerful tool for the investigation of the structure and dynamics in condensed matter samples at atomic and intermediate scales. Neutron scattering can satisfy the requirement of a molecule probe sensitive to structure at 10 nanometer scale, and it has ability to penetrate the bulk of a fluid sample. The realization of the entanglement network can be observed in semi-dilute solution by dynamic light scattering experiments, when there is an optical contrast between solvent and polymer. Dielectric spectroscopy can sum over the chain segmental correlations. If segments of the chains are associated with electric dipoles, when the electric field is applied, the segments will tend to align in a similar way as when the mechanical field is applied in rheology.
Oh, hey there! So far we have learned about the Rouse model, the Reptation theorem, the history of polymer dynamics, and also how spaghetti-like molecules known as polymers behave. But so, does this stuff have any real application in the real world? One application where the Reptation model is very useful is in gel electrophoresis. Here, Reptation theory can help us distinguish between two DNA molecules or different sizes. Since DNA's molecules when dispersed in water are negatively charged, they will travel towards the positive side of a gel electrophoresis apparatus. The DNA molecules will be separated based on their lengths. Longer DNA molecules will move shorter distances than shorter DNA molecules. Since DNA molecules are polymeric materials that can also move via reptation, we can use our knowledge of reptation theory and how far the molecule traveled to calculate the actual size of a DNA molecule. Pretty cool, huh?
Hello, Daniel.
Hi.
I just had a very exciting conversation with Alex. I got some insights about history, development, and theories of polymer dynamics, especially repetition theory of polymer chain dynamics. But this field, as far as I understand, is a growing field. Is there any current challenges of polymer chain dynamics that we need to know?
Yes, it's a growing field and there are lots of challenges that need to be solved. Today, I can tell you 4 of the major challenges.
Thank you. I would like to hear that.
The first thing I can tell you is the tube deformation. In nonlinear flow, it is assumed that the tube doesn't deform. But from experiment, it is evident that the tube deformation is not solely dependent on the rheology. For example, tube diameter depends on the local strain as well. Just think a polymer network which is cross-linked, and the cross-link, what is it? Cross-link is a type of square net formed by polymer change with cross-linking in the nodes at some fixed points. Also consider that it has entanglement. The entanglement considers that constraint deforms subaffinely with the strain. Still, it's a big challenge to find the reason why tube diameter increases or decreases with the strain. Tube also deform at large strain. The reason is not known yet. Knowledge based on simulation and experiment needed to solve all of these challenges in tube deformation.
Oh, that's very interesting.
Now, I will tell you some challenges about reptation theory.
Oh, what's that? Please go ahead.
The simplification of the many chain problem to a single chain moving in a tube of permanent obstacles oversimplified the solution. But in real life, lifetime of obstacles is finite in entanglement solution.
Oh, I see.
That arises some constraints release that was not considered in the original theory. Also, tube dilation occurs in entangled polymers. Due to the relaxation of surrounding change, tube gets wider. Widening of the tube accelerates the reptation relaxation of the chains in the tube. If the long chains are entangled to each other, reptation and tube dilation theory play similar role, but the prediction is different from those theories. Detailed study required to consider the tube reorganization for dynamics of nonlinear polymer.
Anything else interesting?
Yes, I can tell you 2 more challenges. The stress relaxation time of real polymer is shorter than the expected by reptation model. So many researchers try to explain it by constant release theory, contour length fluctuations, dynamic tube entanglements. People are still working hard on this problem. In 2008, Kapnistos and cohorts researched stress relaxation behavior of the ring polymer which does not have chain end. They found the ring polymer, it exhibits self-similar dynamics yielding a power law stress relaxation. And the reason of non-concentrated rings not trap themselves in a melt but relax as self-similar power law with a rubbery plateau instead is still not understood.
Thank you, Daniel, for sharing this knowledge with me. Thank you so much.